the latest values for this Clapeyron slope is 3.5. And we figured out that, I'm not going to discuss this method here. Actually, this method right now, what I'm showing here is semi-empirical and has recently been promoted to first principles, but that makes use of molecular dynamics, which is another story that I suppose Lili is going to discuss molecular dynamics simulations tomorrow and the computational requirements. I hope so. But unharmonic effects can be pretty visible, especially in phase boundaries where atoms are moving. That's when you expect unharmonic effects to be more visible. So where we are heading at, elasticity databases. This is the database, the major database that is used nowadays for some major n-member phases in the mantle, not necessarily solid solution. Book modulus, equation of state parameters, and shear modulus, temperature and pressure derivatives of shear modulus are given. Not they have been measured at the required pressures and temperatures. Not they have been calculated at high pressures and temperatures. And these databases it's a very daring databases that fill the gaps with systematic extrapolations of results when they don't exist. And this is the typical case. These are some pressure derivatives and temperature derivatives of the shear modulus as a function here of the ratio, shear over book, and here shear modulus. So some results exist, and a trend is derived and used to extrapolate results where they don't exist. So, well, we believe that we can fill this gap, and with the aid of the new method that we have developed that's it's more efficient, and VLab, we believe we can generate this database very quickly now. Of course, we have been studying not only with properties, thermal properties within 135 GPa and 4,000 Kelvin. But we have gone to very different materials and temperature ranges. The entire temperature range of the terrestrial planets. We have been studying ice at extremely low temperatures, and phases, oxides, dissociation of the silicates at the pressure temperature range of the cores of the gas giants. And this is a very exciting new area of research. So the major challenge that we face, we needed to study a considerable number of solid solutions, and the calculations are demanding. Some are strongly correlated solid solution, but not all. Thermochemical equilibrium multi-phase systems it's ahead of us. Assessment of the accuracy of new methods and old ones to study new problems. Sampling of pressure, temperature, composition. This generates a very large number of calculations, a job deluge that would be performed much more easily if automated. So from the educational point of view, this is not necessarily new, but it has been expanding very rapidly lately. So recruiting students, postdocs to work in these areas, train and retain them, it is a challenge, because of the skills that are necessary to work in this field. So we will discuss the possibility of establishing tutorials, workshops, and short courses to reach this goal. Well, I think this is all I want to say. Nothing more. I said a lot already. Thank you. Nope. You knew everything, right? You knew everything.
Renata, just one response to your slide on perovskite. I think neither the agreement nor the small deviations are really surprising. The agreement because we're both using DFT, although the functionals were different.
Right.
The pseudopotentials were different. But also some technical details of the calculations were different, and that explains easily. Actually, I would expect much greater differences. For instance, your calculation was quasi-harmonic, and my calculation was anharmonic using molecular dynamics.
Right.
One can easily expect at such high temperatures greater deviations.
Yes.
In fact, perovskite is less anharmonic than I expected.
Right.
It's much more harmonic than one would think. But still,
I think it's more unharmonic at low pressures.
Yeah, so it's one cannot expect that anharmonic and harmonic calculations will give identical results. But still, given that the agreement is surprising.
Yes, I okay. JJ?
You mentioned that in the iron-bearing mineral that you calculation for the olivine and the perovskite, the LD plus U is not necessary. But on the other hand, the ferropericlite is that something to do with the silicon or just iron-iron the distance?
I think it has to do, yes, with iron-iron interaction. DFT gives a metal, and the material is an insulator. It's a Mott insulator. And in the case of perovskite and olivine, you still have a gap. It's small, but it's a gap.
That's because
so the occupation of the orbitals is correct.
I see. And but you also mentioned that now LD plus U, the U term, you can calculate first principle.
Yes.
And with the volume pressure dependence.
Yes.
It's how important, how sensitive is that term? Is that if we let's just say naively use a constant term, are you going to get the dramatic different result or?
Yes, you would get dramatically different result. Of course, you can vary U and test how properties vary when you vary U. But it happens if you have different spin states. It's different U's. It's not the same U for different spin states. So the transition pressure in ferropericlase varies very much.
Yeah, that part I can understand. So the crossover pressure, that one is very sensitive to the U. But for other problems like elasticity, if you or the phonon spectrum, if you use the roughly right range.
If you don't need U, you can vary U, and the properties don't vary very much. But if you need U, it's really important.
So for the elasticity phonon, it's not that sensitive, but for the crossover, is that?
No. If you need U, in other words, if the FT gives you a metal, and the real material is an insulator, then you really need to calculate U for every atomic configuration. It's hard work. But if you don't need U, any U works.
So when you compute phonons, you actually compute the perturbation of U upon atomic displacement?
No. Good. That's a point. I said U must be structurally consistent. As you optimize the structure, U changes when you need U. And phonon, actually, Matteo has not revealed that method yet. I know very little about that. He's going to speak tomorrow. You can ask him tomorrow. But forces, if you need U, forces are incorrect.
So when you do structural optimization, do you update U at each configuration?
Yeah.
And does this affect the result significantly?
We have a paper published on this. Yes, it does.